Good morning. Am I audible?
Good morning, sir. Yes, sir.
Yeah, thanks. Okay, let start. Okay, where we are? Yeah, I have gave some examples. Ask you to try it out, check it out, whether they are sigma algebra, and given a construction, Vitali set which is not measurable. Mm, yeah, that's it. Okay, let us continue today. Further, I think, did you check this? These sets are equal or same? You try with a
Same.
small, you try with a small example, like not even for the functions. You can think of any sequence xn or an, whatever. If you choose a sequence, so uh, you can think of how the sequence is mapping on the real number from the natural numbers. So you take an epsilon uh, around the place where it is likely to be convergent. This is epsilon neighborhood. So this is a plus epsilon and minus epsilon out of a plus epsilon, a minus epsilon. Um, So now you can see the natural numbers 1, 2, and so on. Get a stage n, and let's take a stage another stage small m. Think of it like you know that for given epsilon, this is the stage where it is begins an epsilon. I could say from this. What do you say? Like modulus of an minus a less than epsilon for all n greater than n epsilon. That's what you write. So that means like all these are falling inside this one, no matter whatever you give it. Now, if I ask you the an minus a with the same epsilon, I'm not changing my epsilon, the same epsilon for all n greater than m. This m is much larger than this m is much larger than an epsilon. Okay, that means like now you have to think of where they fall in. They may fall in much smaller epsilon, but I don't care of it. They definitely lie inside plus or minus epsilon because this is my choice. I am not changing this epsilon. As long as I'm not changing epsilon, doesn't matter whether it is coming into this one or not. But definitely it will fall in within this epsilon. That is how this my n epsilon is guaranteed. Okay. So in such case, now, uh, what is the best choice for this one? If I wanted to write one n and one m, do you choose a minimum or maximum? Like if what do you say? Modulus of a n minus a less than epsilon for all. Uh, you don't know whether it is an epsilon, which one is it is starting, or which one it is bigger, which one it is smaller. You just know this information. and you don't know that whether n is before and m is before, or which one is the direction, the order. So if you wanted to write up jointly, what do you write up here? N greater than, what do you write up? I will give you choices. The option A is n greater than minimum of n comma m, or maximum of n comma m. Which one would like to be better?
Minimum, sir.
Okay, why?
Because last class you have explained if after one boundary point any sequence converges in any interval, then um, after if we take after large m, then it will also converges. That's why.
Okay, so you choose a minimum of n comma m, so that definitely the stage you are determining where it is. Okay, that is makes sense. So now you think on that aspect here, the same in the sequence. This is the intuition of maximum or minimum. Why we are choosing minimum rather than maximum? Um, Now you think of what is goes here. Now you have something else here. Just it is a sequence of numbers, but it is a sequence of functions. So every function has its own domain. We are looking for a common domain place where it is falling inside the epsilon neighborhood of a converging function. So now the same scenario, what I explained here last time, this one, you have a n greater than m, you have a n greater than m. Does this d holds the same or differ? Check with an example and convince yourself. Okay, so take your look at our past course last semester, before last semester, the sequence of functions. Whenever you have finished it, you take a simple example and look at different stages and choose a one epsilon and get the different stages and look for the domain, and how do you convince yourself that they are same or differ. uh, that's whatever exercise I just gave you an intuition to follow it up. This is your task now to build up intuition from there and verify with the known examples from our past courses. Okay. So I gave, as I said yesterday, these kind of exercises. I just roughly went through. I roughly give you many things on the way, on the down the line. So it will, you have to exercise on them. So you don't expect me to do everything in the class, because it is not possible for me to. If it is a measure theory or something, the course which we can cover every bits and pieces of it, but we have to cover up a lot of things in this. So you have to cope up with me that you should. You what will happen finally if you don't do it exercises, whatever I am raising in the questions. So you may satisfy by a shallow way, but you may not feel the deep intuitions, or it will block you in the future ahead, like where typical statements need to take a decision, or to follow up with a proof of theorem. So that should be very strong. These building blocks of mathematics should be very clear at at most. The definitions, how they constructed the statements, what they are making, these are all it brings you a lot of concrete evidence, and it makes you easier your job to understand further mathematical writings. So that's it. Now coming to today's Um, okay, so we have discussed a definition yesterday, a sigma algebra, and I will go further today, and mostly I will finish it up this measure theoretic definitions, and we'll touch the how do we connect these things with the neural networks. So, okay, um, let me start with something. I gave some examples, and I will continue with a few more examples with the sigma algebra A3, maybe A4. I will write up here. You check it up. If this is not verified by me, you have to check for whether they are sigma algebras or not. Sigma algebras on RD, especially A is subset of RD such that uh, A is open. You know, open means I don't need to mention again. The RD difference A is open in RD. In between, I could give a or, either or. Okay, that's the one set. If you choose a set, if it is a open or the difference is the complement is also open in RD, then you bring it inside that sigma algebra. That is check for whether it is a sigma algebra or not. Another A5. This is quite interesting. A is subset of RD. Uh, A is dense, or uh, RD difference A is dense. Dense in RD especially. We are not going out of RD. Dense in RD. This one. A4, A5. Open, dense, that you have to apply the concepts. And A4, A5, check for whether it is sigma algebras or not. This is your exercise. Now, yeah, further continue. Okay, another definition, I could say, this one. This is a independent, it's not an independent definition of the sigma algebra, but it is fairly using the sigma algebra concepts. Uh, like, let me write up a fair way. This you know it already from linear algebra sense or group theory sense. The same thing I am deriving. The generator, the collection generated by set of vector generated by set of um, elements in a set, a group, so subgroup generated by some few elements, a vector space generated by a few vectors. The same we are using it here, the in this algebraic structure sigma algebra. Let x be a uh, did I use x for the sigma algebra or something else? Let me, yeah, x, um, non-empty. Let x be a non-empty set. And now what I'm choosing, I'm taking a one collection from power set of x. Some subsets. I'm not saying this collection is a sigma algebra. Some collection, just like vectors from the vector space or some elements from the group. I'm taking it.
Sir, I have a doubt.
Yeah, yeah,
Sir, in the above examples where you have an
yeah.
A4, A5, in those example, what is our X, sir?
Oh, RD is RD. That's good.
So we are taking the power sets of RT.
No, not a power set. We are collecting a subset from the RDs. Sub,
Yes, sir. Subsets of what?
subset of
Subsets
RD.
of power
Uh,
set of what?
yeah. Okay. Oh, okay. I will write up like, of course, everything, whatever you choose, whatever this one, it must be belongs to. Either you can write this one or A is subset of RD. Both are same, right?
Yes, sir.
Yeah. Clear?
Yes, sir.
Okay. The collection is here. Okay, you may have confused. Like here, it is a collection. It is not a just a set. It is a collection. That is a script, not a just a capital letter. Like you think of like whenever I am writing scripting letters like this one or the F or this one. These are all collection of subsets, not a just a set. So that is where I use a belongs to where I use a subset. It is careful. So this is a collection, so that it is a subset of subsets of X. So that's the difference. Yeah. Um, yeah. This is the collection. I'm considering it is from the power set of X. Okay, I will write up like be a collection of X so that you understand. Collection of, okay, collection of subsets of X. Collection of subsets of X. That is hypothesis. Like now I write a sigma algebra. A sigma algebra. I don't say what kind of sigma algebra you choose. Just like if you given any set, you can construct a lot of groups. Similarly, you can construct um, sigma algebra. Sigma algebra A on X. Sigma algebra on X is said to be uh, what I say generated by this collection. The same. If you think of the parallels of vector space, group theory, or sigma algebra, following the same way of definition writing. The only the context and the elements structure changes. That's it. Generated by this collection. If when do we say this is generated by sigma? If um, the same again, that A is the smallest sigma algebra. Smallest sigma algebra on X containing C. The same in the vector space too. If you have a vector, a bunch of vectors given to you, and the vector space scanned by or generated by, you can both the words you can use it. That is the vector space containing the smallest vector space containing that vectors. That is the thing. So same thing here. Okay. Containing the C, the collection. Yeah. This is a simplest parallel definition. Now, how do we look at it? Um, so, what is my point from here is another definition, I could say. The further extension from the sigma algebra. Now, I I wanted to use. mm, the x, here we are using x be any non-empty set. Now I choose just not the non-empty set. I choose a metric space. Let x be a metric space. Metric space. Uh, the sigma algebra on this metric space x generated the uh, by the collection of all subsets open subsets of x is called. Now you understand, everything is very clear here. Metric space means metric space we have discussed last time. And metric, from the metric you can define given any set in the x, whether it is a open or not. That is open ball concept, and we have seen that interior points, all those things to define a open set. So collection of all open subsets of x is called what it could be. A name, very famous name.
So Borel sigma algebra.
Yeah, it is a Borel sigma algebra. That is how the Borel's concept starts from here. And you can say that in a simplest term, you can say that Borel sigma algebra, the definition many people says without using any metric, that what do you say? Can you say in a short sentence how Borel sigma algebra usually defines without any metric?
Sir,
Yeah.
for Borel sigma, it require metric space always.
No, I'm asking how do you define Borel sigma algebra without uh, mentioning the metric? That's what my point. How do you define, like, if you that is what I'm asking the question, that can you define Borel sigma algebra without a metric? If that is, what do you say? How do you define that metric? I mean, sigma algebra. What is your known definition of Borel sigma algebra? If we have one.
Sir, in our sigma algebra, sir, what is the smallest open
Yeah.
subset? That is the
Yeah.
Borel sigma algebra.
Smallest
Open subset
open subsets of sigma algebra
is a
is a
is a
Borel
Borel
sigma.
sigma.
And
Yes,
now
sir.
the concept is, if I given any x to you, how do you define open without a metric? Open definition by you need a metric.
Yes, sir.
Yeah, so that is why I just clearly written here why we need a metric. The open doesn't have any its own specificness unless you say it is come through a metric.
Yes, sir. Understood, sir.
Yeah, that's it. Okay, usually called Borel sigma algebra. Uh, Borel sigma Borel sigma algebra. So that's I can write up other way of saying, very short way without writing all these things. You can say simply Mm, the smallest sigma algebra, smallest sigma algebra containing all open sets of X. That's it. But by convention, whenever you are saying open set, there must be this X must be either a metric space or a topological space. And I don't think you have come across a topology, but that's why I did not touch. Usually, in general, metric space is a common thing, but usually write up a topology. So forget about the topology sense here. We don't touch in detail. Okay. So this is the sigma Borel sigma algebra. You can say it. Now let us see some characterizations of the Borel sigma algebra, especially in RD. Mm, um, okay. I just wanted to give some collections. Uh, I'll write up with C1 equal to A subset of RD such that A is uh, closed. So now what my point is, this is a collection. This is not a sigma algebra. This is something like this C, whatever I'm talking, this C from the power set of X, subset from the power set of X. I'm collecting all the closed sets from RD. Now what I'm asking, let's say the A1 L or otherwise AC1, I could write up A algebra generated by this collection. Okay? Algebra generated by this collection. Is this collection uh, is a Borel sigma algebra or not? Okay? So this, so now you have to say that uh, is is a like uh, Borel of RD. I'm writing this one Borel sigma subset of Borel subs. It is if it is if this ACI is a sigma algebra, then whether it is a Borel sigma algebra or not, this you need to check for. And another collection, that means you just go with the ordinary definitions, like you don't, metric space is open, that's you know it, A is closed, I have given the collections. So now you have a C1, then now we have to think of the sigma algebra generated by the C1, whether that sigma algebra is only having all open subsets of RD. That is my question, whether it is a Borel sigma algebra of RD or not. So that means does ACI is all open sets of X, open set, so open subsets of RD or not? Other way of asking. Another C2, do the same repetition tasks kind of thing. So for different collections, A is subset of RD such that A is compact. Compact, you know it, for the same, repeat the same task for this one too. Um, A is subset of RD. Now I slightly modify this first one. It's A is a closed set, but now A is A is closed D box. These two are two different things. Closed D box and closed set are two different things because the D box has its own characteristics. That is a kind of like we have defined D box, but it doesn't follow that D box definition. Any closed set. It's a closed D box. Closed D box means whatever you in 2D, if you take a D box of let's say A comma B cross C comma D is a D box for any A B C D real numbers. So this is a closed D box. But if you choose this one open intervals, that means you are not involving what is called this one, but the boundary is not involved there, so this is not a open. So that is how it is different from the closed dbox and open dbox. Another C4, same extension RD. All examples, all the lists what I'm doing, if you know, if you do it, try it for one thing, and rest of the things are very quite evident because all are slightly interconnected. A is uh, an open dbox, and C5 a collection, just a dbox, and just collecting A is a dbox. A is a dbox. If you choose all the dboxes from RD and if you generate, then do you get only open subsets or not? That's the thing. If I do have other, I'm not sure. Let me think. Okay, let us write up. So why not open dbox? In general, dbox is in general open sets. Like A is subset of RD. A is a open ball. A is an open ball. Now you may ask like what kind of open ball it is. So that depends upon what metric you choose on RD. You require a metric on RD. So you can think of like usual metric in RD instead of choosing any usual metric. You know it. We have defined the usual. The metric D is what is called Cartesian distance metric that you can take up. In there are several other metrics you can define, but usual metric, yeah, Euclidean distance. Mm. And another one more. You can try all things we have seen these things in um, our metric space. So the F inverse of W such that F is a mapping from RD to R is continuous, and W is subset of RD is open. Now this is a very interesting one because we deal this one in our neural network. So what it is saying, you have a RD, you have R, a mapping, a function is a mapping from RD to R. You have a open set here. That is, let's say W is a open set. This is subset of R. And now the inverse image, that is here, F inverse of RD, F inverse of W, that is a subset sitting inside RD. I'm collecting all those subsets for every open set in R. whether this C7 is a Borel sigma algebra or not. Not C7, and the sigma algebra generated by this C7 are a Borel sigma algebra or not. That means it does it cover all open sets of RD. That is the one way of saying. Okay, you just get a feel of intuition from the definitions of D-box, open sets, and open ball, or the continuous definition, and just try them out. Uh, yeah, this is all about. I think I'm done with this sigma algebra, basic construction of definitions. Maybe I will start something new out of this. I'm just thinking, does there legible things to discuss further? Okay, I will define something.
Sir, in the above example, W is subset of R. No?
Yeah, W subset of R.
But in the
Okay. Yeah,
collection,
yeah, 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 yeah. Right, you're right. Yeah, and W subset of R is open. Yeah. Okay, fine. Um, I will define another definition on based on the Borel sigma algebra. It is connecting now measure, that is let x comma a sigma algebra, whatever the sigma algebra you choose, a be a measurable space. As I have already told you, this is a measurable space. um, I could say a function. Now a function I just take mu from sigma algebra to 0 to infinity. I think I have given some kind of intuition for this, but I don't know whether you have tried out or not. I asked at very beginning a question that now I am bringing that question into some kind of definition. Somewhere I have asked, if I remember. Yeah, yeah, this one. See, this one, can we define a function mu from power set of RD to 0 to infinity such that all the measure properties, whatever the very nice measure properties, should satisfy, like the set whatever you are taking, the measure must be volume of a D box, and if A is subset of B, then measure of A less than or equal to measure of B, and if you have a union of pair weight disjoint sets, then definitely they should measure of those unions must be equal to sum of their individual ones. Can we have a such mu that on the question you if you tried out, then the definition is now in the form of a kind of formalizing into a form of definition. 0 to infinity. So now you think of like I have included infinity also here as a closed box. Usually infinity usually keep it as a open, but I'm keeping it as closed because there is some essence to it. Because that example also we have seen that like measure of the whole RD is also is infinity. So that infinity concept it is extended. So that is infinity being involved into it. So we are not saying that infinity is indefinite or undefined. We are saying infinity is being taken into the consideration to say that measure of a set can be infinity. 0 to infinity is called a measure. This function itself a measure on the space, the measurable space x comma a, if if uh, first condition, that is same whatever I have gave the question, that is mu phi equal to 0, measure must be 0. The second, countable additivity, that is measure of union of n equal to 1 to infinity a n must be equal to summation n equal to 1 to infinity measure of a n. I could say if I don't know how do you write up a1, I will write up explicitly, right, and so on, belongs to sigma algebra A or pairwise disjoint. Pairwise disjoint. Then these two are sufficient to say in the definition. I don't need to mention that inclusion one. That by this second one it is obvious. So if mu is a measure, if this is the definition for the measure definition, whatever I said here, measure definition. Suppose now the point is, if mu is a measure, if mu is a uh, measure on a sigma x comma a sigma algebra. Now I extend the definition of sigma algebra x comma a to the triple now, the triple, the triplet, I could say, the triplet x, the sigma algebra, and the mu. The measure also is a function which is satisfying these two properties on the sigma algebra when this is called a measure space, is a measure space. All the definitions are fundamental is sigma algebra. These are all continuing to the sigma algebra definition. So now you think of like very first beginning lecture where we started with the smallness and bigness of the sets with the measure, how do we measure, all these things were answered here with this definition. So far, where we started and we end up with a definition, why the sigma algebra is making a nice collection so that they are comes under a safe hood in the terms of sigma algebra, where measure is very perfectly defined with these properties. So with this, I think the measure on the measure space. This is so far whatever we discussed. This is not the content or not the syllabus of our neural networks, but this is a prerequisite for, because as you haven't done measure theory course, so I took a small intro on this measure space, very shallow level, but you can read further. There are a lot of other things I'm not touching. Otherwise, it keeps pulling our leg to uh, keep stay here only. But there are a lot of types of measures are there. I think whenever you have a course on it, or you may have uh, mm, future interest, you can read further. Okay, now I will slowly move. Okay, there is we need this is almost everything we have done from the measure theory, maybe one or two left, but that is quite evident built from the whatever we know as of now. I'm just thinking whatever left. What else? Maybe measurable functions we require because the functions mostly we deal with in the neural networks. Um, but measurable functions. So that is okay. I'll write up that definition too. The definition, which is a measurable function, that is called a measurable function, which is quite similar to the continuous definition, but it is in terms of sigma algebras. Let's say let you have a set X and a sigma algebra A, and you have a set Y and you have a sigma algebra C, be two measurable spaces, measurable spaces. Now a function f mapping from X to Y. You can think of like in the group theory, we always have a function g 1 comma star 1 to g2 comma star 2, like this. The two algebraic structures, homeomorphism, we have defined like the same. Now it is quite, the structures are now sigma algebras here. X to Y is said to be is okay. Now AC measurable. This is a quite like it is completely depends upon what sigma algebras you are choosing in the domain and codomain. AC measurable function. AC measurable function if it is quite similar to the continuous definition. F inverse of C, capital C, uh, belongs to the sigma algebra A. For for every C belongs to collection C. It is quite simple. Like we have two sets X and Y, and we have a function. So you have associated sigma algebra here. You have associated sigma algebra here. So if you have some C, which is the C belongs to this sigma algebra, then if you have this inverse mapping, whatever inverse mapping you have, this one, if it is belongs to the sigma algebra in A, the pre-image of uh, s- element in the sigma algebra of codomain is belongs to the sigma algebra of A, the domain, then we say that f is a measurable function. It is quite similar to the continuous definition. What do you say in the continuous definition? If you can analogy in the continuous definition. So X is a set and Y is a set, and if this is a open and if this is a open set, now you choose a pre-image of this open under the F inverse, and then this let's say this one is some C. F inverse of C is open for all C, then this F is continuous. You understand these two analogies? Now the continuous is extended to measurable. Okay. Now I will ask a question on top of this one. It is very, very, very uh, interesting and So a lot of work we can avoid the connection between these two. If I have, if I say x comma a function f from x comma sigma algebra a to y comma sigma algebra c, and this is if f is measure function or measurable function, measurable function, then f is continuous. Can you say this one? Can you say? Think of it. Everything, all the things so far we have done. Now this is a very uh, why we need measure instead of continuous, and does continuous space is sufficient or not to deal neural networks or whatever? Which one is collection of who's, like which one is bigger? The the open collection is oh, this one especially discussing open collection, this one especially discussing the measurable collection following the set algebra, and now what it is tied up both closely. Can we say this one? If we can say in what conditions and what circumstances are conditions we should consider further. You know it already, but you just a little bit think. Why what continuous is dealing about, what measure functions are dealing about? Measure functions are dealing about the functions of inverse images of every sigma algebra uh, element is mapping to the codomain sigma algebra element. The pre-image of sigma algebra element is a sigma algebra element. And here the continuous functions is, you know, the definition, the open set of a codomain is inverse pre-image or pre-image is again an open set.
Sir, if collection A and C are Borel sigma algebra, then
Yeah,
it's
exactly,
fine.
exactly. Yeah, right. You got the point. That is how the Borel sigma algebra we define here. Like the Borel sigma algebra, it is the discussion, whole discussion. It is talking on the collection of the sigma algebras are containing all open sets. So now, if you know that the space, if you are consider is a Borel sigma algebra, then we don't need to worry about the whether it is the measurable function, or like we can directly shift to the continuous theory instead of measure theory. So if it is not a Borel sigma algebra, it is a pure sigma algebra, then we have to stick with um, the sigma algebraic notion of this one, the measure spaces, measurable functions. This one. So now, I think you got the connections where we started with the sigma algebras and the measures, the set measuring, and all the way down to Borel sigma algebra and how it is connected to continuous functions. Then, okay, I will write up a statement with this. So, having, okay, maybe it's not a definition. If x comma y or metric spaces, I will write up metric because it is always open, require a metric. So, x comma y are metric spaces, then every continuous function Uh, every continuous function f from x to y is I could say the Borel x, the Borel y. That is, Borel x is the sigma algebra of the domain, and Borel y is the sigma algebra of codomain of the function f. I mean, the sigma algebra is defined on domain and codomains. Uh, the function is bx by measurable. That is how we have defined AC measurable earlier. The same way, AC measurable somewhere, I think, yeah, we have written here. The AC measurable function. This now this f itself is a bx measurable if x comma y is a metric space, and every continuous function doesn't matter. Like every continuous function is a um, um, bx by measurable. Okay, that is we have to think on, like continuous is coming into the picture whenever we have Borel sigma. This is the connectivity between Borel sigma algebra and continuous. Mm, okay, that's it. I guess, like a lot of other properties are there. That doesn't we don't require much properties as we are. mm, okay, maybe we go with some uh, the sequence of functions. The function sequence of functions little bit on top by using this measured sigma algebra, so that would be a recap for our sequence of functions. I will write up. I don't discuss too much on them because this is most of the things you know it, but I slightly use the sigma algebraic way of discussing this convergent functions. I'll write a definition directly. So you will understand very clearly. Let x comma a comma mu we just defined is a be a measure space, be a measure space. Uh, we say something if there is if there is a belongs to sigma algebra a with the measure mu of a is zero. The measure is zero. Uh, give me a think. Hmm. There is some definition almost everywhere measure. I want to just define almost everywhere. Hmm. With measure of a equal to zero, hmm, and mu of oh no, it's not the thing. Yeah. Let me rewrite something. measure space. Mm, okay, I'll write up instead of just measure on a particular element. I go with a definition of something on top of the function so that it is much better. Mm, okay, let me write for functions. Mm, okay, I'll write if functions. If functions fn and f, the sequence of functions fn and f both are mapping from x to minus infinity to infinity, I could say. Functions fn and f mapping from x to minus infinity, we say that the sequence fn converges to f. That's usually we write fn, this one fn converges to f. Same thing converges to f uh, point wise. Of course, we have to mention point wise, and not just the point wise. You know already what is point wise. I just say another extension of that one. Point wise, mu almost everywhere. Mu almost everywhere. That means most of the time we write like mu ae, mu almost everywhere. Um, if there is a set A belongs to A in the sigma algebra with with measure of that A is zero, such that Fn converges to F pointwise on X difference A. This is important. Like just what I'm saying, actually the fn converges to f pointwise. That is up to there. It is very clear. But now another a piece of bit extra thing is being added here. Pointwise is fine, but mu almost everywhere. F is pointwise with mu almost everywhere. It is especially saying wherever converging function is lying, or where it is happening, that is should be on the not on the measure where it is zero. So that means like you should you should land up pointwise on x difference a, that is the domain out of non-measure, I mean zero measure. Out of zero measure you have to land up. That is what we say in such cases. The fn converges to f pointwise mu almost everywhere. We require this one whenever you have the landing place of this one, the functions, wherever the domain, whatever we have defined, like this one, right? The set of x's fn converge to f. So this is some set. Let's say this one is your p, or a d. So if there exists a set A, subset of D, such that the measure of A is zero, then You understand where we are touching now? So if there is a subset of D where measure is 0, then what could be the scenario here? So if the measure is 0, you cannot able to quantify the domain properly with the in the space where it is occupied inside the D. So there are bit of measure the you cannot able to quantify the data or quantify the points with the proper justification where the measure you defined it is giving 0. So that is where we are taking care too much in the definition sense, at least in the theoretical sense. um, F is the point-wise mu almost everywhere. That means whatever measure function you choose, that is you're saying like if there is a subset of A with measure of A is 0, such that Fn converges to F point-wise on X difference A, then we say that mu almost everywhere. Almost everywhere. So the point-wise definition we are extended to further line, that is mu almost everywhere. Like as we have the denseness, you can relate the analogy with this one where almost everywhere dense or somewhere dense. The similar context you can think of like the point-wise convergence is also a almost everywhere convergent. If there is something a set of measure is sitting inside our with measure 0 in our domain, but somewhere like you see this is our D, then you have identified some with you, this one measure is 0 for this one, but there is no problem outside of this one, then we say this the function f is fn is converging to f on this domain on this one, then it is not everything but at least it has its own measure 0 part, but still we say that almost everywhere convergent on the point wise on this particular region. So this is when you are saying, when you are not saying this almost everywhere but you are saying just a point wise, that means there is no such holes, there is no such singularities or bad points or where the measure is behaving null. So this is a kind of like theoretical sense of thing, but we see in the neural networks very closely, almost everywhere things, because our data where we work on the data sets, most of the time we have to segregate, or most of the time we have to see our metric or on the considered uh, definition should follow up with this one, like what are the parts we are removing and what is the measure on it, and should we take a decision on non where the measure is 0, or how what is the measure of outer thing like other than x difference a, that these are quite relevant to talk on whenever we are discussing the neural networks there. So that's this one of the definition which we quite most of the time we touch the just not the point wise almost everywhere. So whenever I say point wise is point wise, almost everywhere means that you should remember a kind of this definition. Yeah, these are all little extensions, uh, requirements, and I'm not touching the anything of sequences definitions. Maybe you know it already. Okay, maybe I will discuss one more definition of the same which you know already, the point wise definition. Uh, uh, the sequence of functions. Okay, what else? Right, let x a mu be a measure space, and let fn comma f or mapping from x to real numbers be be measurable function. Be measurable functions. We say the first point. I could say we say the sequence fn converge to a function f in measure in measure. Yeah, you know it already. How do you say? If for every, okay, I need to choose some mm, symbol for every epsilon. I don't use. Yeah, no problem. I can use epsilon, but epsilon we mostly use for something else. But okay, let us use epsilon. No matter. For every epsilon greater than 0, we have limit n goes to infinity, the measure of uh, the measure of the set which I have defined this one already. X belongs to X such that modulus of fn of x minus f of x less than, or not less than, let me choose greater than or equal to epsilon, greater than or equal to epsilon is 0. There is some missing version. This is a set closed and measure closed. This one, set closed and measure closed equal to 0. You understand what is this? This is the another way of saying Fn converge to F. The convergence definition. Fn
Yes,
converge.
sir.
Yeah. So can you relate this way of writing definition to our known definition? Can anyone explain me? Your known definition is what? Your known definition is modulus of something like Fn of x minus f of x less than epsilon uh, for all n greater than or equal to n for given epsilon greater than 0, right? This is our known fundamental definition. So now I am asking, how do you think of these two, or convince yourself the measure theoretic way of writing? There must be, obviously they match. They should match. Or otherwise, I will write up another way of writing. This one I will keep it in different colors so that you will know that. Mm, I'm writing that one into different one. Another way of writing the above one is if uh, for all epsilon greater than 0, there exists there exists a capital N belongs to natural numbers, that is the stage, such that such that measure of measure of x belongs to x, such that modulus of fn of x minus f of x greater than or equal to epsilon is less than epsilon. The measure is less than epsilon. Yeah, uh, for every uh, for every what capital N, no, for every n greater than capital N after the certain stage. Now tell me, I don't spoon feed every detail because you know already the measure definition and you know the sequence definition. This is our known definition. I just given very shallow way. It's a point wise, and I write in two different contexts of these two are same. And now how do you look at the three versions are the same? I just little extended this
Sir,
one. Yeah.
the last third one, sir, if we already know if our sequence of function is converges some function fx, then for every epsilon greater than 0 after a certain difference between sir less than epsilon, na, how it will be greater than epsilon in third last one, sir.
Yeah, okay. This as I'm not talking. That is what like the kind of here. Not only last one, this one also. It is a greater than epsilon. It is also greater than epsilon. Now think of this one. Uh, I am looking at the collection of all the x's whose are out of the epsilon bound. I am collecting it. Those measure must be less than epsilon. You think of it.
Okay, okay, sir.
Understood? Yeah. So now tell me what it is strongly saying about the known thing we always see like we are the function convergence always sitting inside the epsilon bound, but measure what we are thinking. We are thinking out of the bound. Like okay, let me draw the I used to draw from very beginning. This one like you have several functions and let's say this one, let's say this one, what they are doing, you have epsilon band some epsilon band here, and now you see uh, some kind of some stage where all the functions are falling out. Now these are all the functions which are in the epsilon bound, but now the functions are which are out of the epsilon is this one, right? The out of the epsilon is this one. The functions those are like this one, those are like this one. So now get those points. Get those points where the functions are not falling inside this domain. You understand that in this epsilon band, and collect those excess, those collect those function domains where it is not falling inside the epsilon. That must be those, the domain part, the region where the functions are not falling inside the epsilon domain, in the epsilon band, or the measure of that domain must be close to zero. That is what it is saying. The size of the set, the size of the domain where the functions are not falling inside the epsilon domain, epsilon band, should be, measure must be very less. Measure must be very small. It should not be too high. So that we see for every n epsilon, okay, of course, the as n goes to infinity, that must be zero. That's what it says. The measure of that domain, uh, the falling out of the epsilon band must be zero. So now the question is, how do you think of these two, or convince yourself that these two are equivalent? Saying in the continuous sense, or saying in measure theoretic way?
Sir,
Yeah.
sir, we already know, sir, कि if our function is converges from sequence of function to another function after a certain stage, then we already know कि all the point goes in that epsilon bound. If
Yeah.
any other point which is out of the bound, that's
Mm.
also maybe we can say small, their major is very less,
Mm.
like that. Because
Yeah. Yeah. No, that need to be concretely think on how it is. So you take an example best, like you choose like fn of x equal to x raise x raise n or something. So you try it. So apply for both the things, like fn of x equal to just like x raise n, um, as n goes to infinity, x rise n, and of course um, on take 0 comma 1, this is our x, and then where does this converge? Which function
zero,
is
sir. Zero.
0? Fn converge to 0, the 0 function. So now think of like
If
how,
x equal to zero, sir,
yeah,
if x equal to zero, then it will convert to one. If x and if x equal to one, then one की power infinity.
yeah, like
It
you
will.
can, yeah, so you can say this almost everywhere by writing up.
Yes, sir. Yes, sir.
Yeah, as you can take the leverage of definition. So like if it is only 1 point, then that is what I said, right? If it is only, almost everywhere convergence to 0. So because whose measure is 0? Yes, measure of 1 is 0, no? Measure of 0 is 0, the element, right? Yeah. So it's almost everywhere definition you can use. Yeah. Now we try with taking different epsilons, and look for whether the measure as n rises, as n goes to infinity. Maybe you can write up a small program, keeping n is as much large as n. How you look at how this measure of that one is 0. The measure, you know it, like the measure itself here, it is the length of, here it is a simple belongs to r, a subset of r, so that it is just a length of the interval, the measure is, right? So you just try it, this one, so that you feel comfortable. The measure theoretic way of the functions are converging, sequence of functions are converging to a function. Okay. Maybe I will discuss further the representation theory. There are a lot of other theorems are there, but that's okay. So this is, I think, I feel like almost I finished the measure introduction. I don't say that it is entire measure theory. Um, so you understand why we are discussing this measure, to understand the data sets very well. When we are trying to look at for a solution, or a training algorithm on top of a particular data where it is converging and looking for a steady solution, that must be concretely built on the of course these are all theories, but the theory we satisfy a lot, uh, because the makes theory doesn't have any flaws in it, and these are all theoretical assumptions. But whenever you transport this theoretical phenomena into the practical approach, where you see a lot of disturbances, like whenever you say Lebesgue measure here, it is a theoretical sense of definition because it is a infiniteness, but there is no such infiniteness in the computational theory, algorithmic writing. So we write infinite notion every time here, and a continuous notion every time here. These are all doesn't exist in the computational writing up. Like whenever you bring it down to the level of machine level writing, so a lot of things are faded away. So you see a lot of struggle when you are writing a program. Why? Majorly, that is why we haven't reached artificial intelligence or machine learning or solving all problems. We see a lot of problems it doesn't understand, doesn't solve, doesn't able to capture the patterns in it in a lot of areas, because of there are a significant huge void between theory and bringing down to the practical level. So once we discuss the theory of neural networks and applying this measure concept in the neural networks with the proofs and evidences, we see, like, the world is doesn't have any problem. We can solve every problem in the world, no matter whatever it is. But that is not true. That's we have to always keep in our head. uh, Mathematical theory, of course, that this is the theory which is forcing to bring it to some extent in the computational way, to solve a lot of other things, even a small region of problems, and with some epsilon margin of error. And that's a day by day or year by year, we are trying to converge our solution procedures or solution models into a much narrow band, so that they are approximately solving uh, many problems. So uh, this course, as I said very beginning, as most of the time we discuss on the theory, uh, it will understand you how mathematics is so strongly built, uh, these advanced technologies. So this how this measure theory or uh, fundamental real analysis is sitting with hidingly behind the complete architecture of this artificial intelligence. That's you will feel that. And where do you use, but I don't say, You may not use directly when you are whenever you sit on a computer program. You don't start with any Lebesgue measure or something. You just start with some model or data. So these things are hybrid and uh, converted into the a kind of a space that is a bit annoying to understand the lag between theory and practical. And if you see that real void, how this theory is really working and how this practical approaches or why they are failing because of these gaps, then you are done. Like you are understanding the complete world of the artificial intelligence or machine learning, anything. So you may not know the intricacies of complete details of internal stuff, but you know it exactly what's happening. Uh, you may not write up in a expressive form of mathematics, but you can feel that okay, this is the reason, this is the theoretical evidence, this is the practical difficulties that bridge it enforce you to in the future, like to study further deep down to the lines of uh, uh, research or kind of fixing the issues until you reach a point. So this course, I'm not sure, like I don't touch any programs or I don't touch any, maybe I'm not sure. Like I will give most in the form of exercises for you to check it, theoretical evidences or theoretical results and practical approaches, and look up for the gap, how theory and how practical or how computers are behaving with the theory. This if you could see very realistically, then the purpose of this course is well maintained or uh, um, well settled, I could say. That is the point. Otherwise, knowing just theory without touching practical difficulties, it, you don't feel satisfied. uh, so I think I hope I can keep you that point. Sure that you see the training procedures. I will give. Maybe I may not write the codes up for you, but you should engage at some point of time with balance with the theory and practice. Okay. Yeah, another couple of minutes. So I could start with the neural network definition, or not definition. I will just give a rough. I don't know, whatever things comes to my brain. I will just tell you. I am not have any plan of motivation or introduction or something. Uh, Maybe I will just start slowly. Uh, So I'm sure that I well given the enough information and make you understand the measure and Lebesgue sense of measuring the sets, and the sigma algebras. Why do we measure the sets? Why do we sequence of functions are converging to a function, and the domain where the functions are converging? At least you know that why we are studying these things. Are you?
Okay, sir.
Yeah, I'm just asking, like, be interact with me to discuss so that you will be exposing yourself into the world of knowing many things. If you be silent, no, so that I just uh, it will be kind of a passive thing. You just interact or ask many things so that the discussion brings you too many things on the way. Otherwise, I will go with my own ways. If you ask me, it will be active one. If you don't ask me, it will be a passive one. So that's up to you. That, like, I do, I see most of the time you are just silent. when I ask questions, or you come up with a volunteer way of discussing a philosophical sense or theoretical sense or practical sense, whatever. So it is not just the course of regular semester to write for exams or write for grades or something. It is a kind of a journey to understand beyond the subject, beyond a lot of other things. Like it is not just a course; it is uh, beyond a lot of other emotional aspects too. Like I could say. So because sometimes you feel like how machines got a life with this simple mathematics, and also you may reach a point of state of mind that uh, the intelligence behavior of a system or a machine, uh, the mathematics, you feel so dry how this mathematical rules are functional, what do you call, like theorems or statements or definitions, making the machine to think on its own. It is not just a thinking, it is just mathematics. It is just the way of mathematics is being uh, developed or being concretely evidented in the rules. So the computer applications, whatever machine learning or whatever learning, it is just a tiny piece of application out of this concrete mathematical world. So uh, if you come to that state of mind of, like, the you don't like, I could see people think of artificial intelligence or machine is thinking on its own, machine is doing on its own tasks. You feel like, I don't know, the state of mind of people who doesn't have any uh, mathematical material, which is cost to the building of those systems. How do they think? That is puzzles me a lot. Like uh, how a person do think on a machine which is thinking on its own, which is doing a lot of tasks. It is singing, it is creating images, it is creating text, it is creating stories, it is creating music. Uh, can anyone tell me in a sense of uh, the way, the people who doesn't have tech background, at least even they have tech background, but not a mathematical background of building blocks of those technologies, what do you think of, how do they see the world? Do they see mesmerize, or do they kind of like, yeah, machines are learning? Are they really machines learning?
Sir, if they
Yeah,
are not belonging to tech background, so they
yeah,
don't see कि message is learning, sir. They see
okay,
कि it is a magic kind of thing, sir.
okay, yeah, like, of course, yeah, it's
Actually,
a, yeah, it's a
like sir, if
magic,
if I belong from commerce,
yeah.
like art side, sir, and I don't know about any kind of coding and how we build app and how we build models, then
Mm,
I see कि this is a kind of magic, sir.
okay.
We can get all those things from one prompt or something
Yeah,
like that.
yeah, right. Do they feel like the machines are really behaving like human learning? Like, do they think like, as we think, as we have a natural intelligence and thought process, and do they think the same as they are alter humans or alter egos of humans? So does it have a life? Of course, it doesn't. Like uh, the the wiring, we have the behavior things. This this is a quite philosophical way of experience for and of course, if you go into the mathematics, what will happen? The state of art you learn from the mathematics, which is caused to those technologies. If you understand this mathematics, you don't feel much fascinated. You feel like it is nothing. It is not doing much. It is not doing as you know. Because mathematics is says not sound very uh, strongly that the computer is learning. So you feel the learning of artificial intelligence, whatever machine learning is doing, you feel like so bad. Why? Because that doesn't satisfy our known ground rules of mathematics. Of course, it does, but it's still lot of struggles it is making. Because the one thing, the problem, the fundamental problem, not to bring up to a level where we can. There is the arguments called. We may reach a point, the supremacy, where the point from that point we may not improve our systems. That is even still bothering with the artificial intelligence world. We don't know yet actually whether we have reached a supremacy or not. At least mm, in Western countries like Europe or US, as of now, struggling a lot to improve the models or design something new so that which is at least uh, solves the problems of much accuracy and expand to the lot of other areas. But unfortunately, it is not happening. So I'm not sure whether we have already the world we need reached a supremacy or not until or unless some breakthroughs come up in next few uh, down the line of years. So that is a bottleneck we are really struggling. Uh, of course, the whatever we see that is so good, but there is a lot journey. No, we are not sure that we will understand.
Yes,
Um,
sir.
yeah,
Yes, sir.
yeah, that's we will understand soon. The we will prove some theorems. The theorems will tell you lot sound so heavily to discuss. Okay, maybe I
Sir,
yeah.
sir, will we do some coding part also in this course like previous semester, sir?
That is maybe I will see because I'm not had planned anything of coding, but we will go with the toy cases and some examples, particular cases. We will do, of course, to understand what we are discussing and to see evident in the uh, computers. But mostly we discuss the theoretical side. So first, at least this month or next 2 weeks, we stay in the theory. Then we slowly touch with how those theories are transformed into algorithms that you should know at least some extent. So you are just simply calling a function and doing it, but how that function, how that model is working behind the lines, that at least you should explore. That is what you should not feel like you are just applying a black box setting from the models. So you should be in the position that like okay, if you wanted to do or implement a new model for your own kind, you should start your own package or your own model. That knowledge I can assure that you can start with after this course. So
Okay, sir. And
you don't feel like a blindfolded with a lot of models around our world. Of course, there are hundreds of models are there, but if you wanted to build a one, and you can do it.
okay, sir. Sir,
Yeah.
sir, how after studying this theory, sir, how can, we are able to relate last semester like affine function activation, all those things,
Yes. Yes.
sir.
Yeah.
The
Yeah.
last
Yeah.
yes,
Yeah. FN
last
functions.
semester you have
Yeah.
provide one complete code of neural network, something like that, sir. Then
We
uh,
will come to
you
that. We will come to
okay, sir.
that,
Okay.
and we will discuss not only just that one, and I will discuss that is a artificial neural network, I guess, ANN, right? Am I correct? Yes.
Yes, sir.
Yeah.
Yes, sir.
So we will see like different architectures and different structures of one, not just that one. In mathematics, in mathematical way of writing them in a set theoretic sense and functional way of representation, so that you have a lot of tools in our hand of set theory and functions, so that you can mix and match, or you can you have the lot of ingredients of mathematical ingredients. Now you can cook your own recipe to bring up with your own mathematical model. Let us uh, discuss this. Create a new mathematical model. Once that mathematical model is being developed with your own way of thinking, then next stage is bringing that mathematical model into the coding part. That is second thing. So not just the existing models like ANN, CNN, GNN, whatever so far you might hear, you can define your own name with your own way of writing. So you take a pen and paper and you can start with your own way of writing a model in mathematics. Then that's a model, you can name it your own name for your own sake of. Let's that is second part, like whether how it is working, where it is working, what kind of problems it solves, and how do you see that. That is complete way of your own thinking. So, uh, you can define hundreds of models just by mix and match. Like given ingredients, one can prepare a lot of dishes with a different tastes and different variety of flavors. And same thing. Like you have all the things in front of you, you just cook whatever you want. You will reach that point in next maybe 2 3 weeks.
Okay,
Okay.
sir.
Yeah.
Okay, sir.
Okay, then we'll fresh start with the next week, the discussing this neural networks, um, mathematical sense. I don't touch with as of now. The definitions in mathematics completely lies in, and
Sir,
of course in the measure theory. Yeah, yeah,
sir, I have two questions.
yeah. Please.
Sir, first one is how close are we to AI replacing humans, or tech companies call it intelligence? Like, I want your
Hmm.
perspective of how close we are to that. And second question is that, sir, how do you remember all these definitions? Like, how they stay in your mind?
Okay. Okay, okay. First of all, for the first question, I'm not sure of it. Like even I thought of several times how close we are. Uh, that's what I earlier when I discussed just 10 minutes before, like the supremacy of artificial intelligence. I'm not sure of it actually. This is because whenever I start with some exploration of in this direction, where we are right now and how fast it grow up further down the line, that is mesmerizes me a lot of times. Like we are do not have actually a because a lot of independent bodies, a lot of independent research is extending. Uh, Now, currently, what I could see from my perspective is uh, the general idea of whatever so far we built, it is expanding into the all the domains. That is what currently is happening. It is irrespective of the domains, it is expanding. There are two latents I could see. One is expanding to all the domains. One second part is evaluating itself. The technology evaluating itself is one parallel and expanding into the domains. These two are out of these two, expanding to itself is slower down last few years, and but expanding to the domains is rapidly going. it is exponential, and of course at after a certain stage it will reach a peak, and again it will, the graph will fall off. But again, I feel definitely in the next a decade or two, uh, there should be again a peak of intelligent systems develop on its own and evolve into the next level. That that I cannot say what time bound, how close we are. The next second one, you are talking about the definitions. Really, I'm not sure. Like one thing, the way. Okay, you ask me right how I am writing this one. Suppose let me take a one piece of example. Let's say this one. Hmm. Before writing this one, what goes in my brain, especially, uh, I don't see the text. And I don't have any textual writing this one. Only I have a kind of like a pictorial information of this kind of thing. Just what is function, like the sequence of functions, where they are falling, where, I don't feel, I don't feel just in the 1D or 2D. I just think of them in the higher dimensional setting. We cannot think in that sense, of course, but there are manifolds or higher dimensional functions or setting in the they are going or converging FN in a certain domain region. All these things pictures, pictorial way of imaginations, uh, those when I am trying to write up in that I try to maintain the details, what that picture is actually defined for, what that imagination. I don't call it as a picture, it's a kind of I cannot draw entire imagination whatever I imagine in my brain on the pictorial form. It is a projection. Only I can able to draw it. That 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 imagination drawing brings me into the textual form when I am writing in front of you. That's the short answer. I could say I don't remember actually the text. If you ask me suddenly the definition, tell me. I feel definitely I can't say in textual way of writing. That's why I take a lot of time to write up. Like I process that imagination into textual. Maybe there are little flaws, but small flaws. I don't think of that violates the definition rules. Yeah, that's that. I answer like, what do you want from that? So, how do you think of definitions, or how do you? Because the definitions, I don't think of it is just a definition. It is a construction of some conceptual idea. It is concreted and proved, or it is become as a concrete, a building block of the conceptual setting. That's what I could say. So, if you repeatedly do the same thing, whatever I do, that way of imagining the things, and then it will become automatic to you. So you don't need to remember anything. If you are remembering means that is not the thing. So you should think of in the rules, frame the rules in a way abstractly and pictorially. That is the only thing. So what laws governs that rules, and those laws should be. I don't think those laws I don't remember them. Though those become evident, or maybe it become into a kind of a muscle memory after a certain times of thinking deep intuitively, why that is happening, asking several questions on the definition, asking several counter examples, and asking yourself to give non-examples, and where the corner cases when you fix try to do these lot of other stuffs. around the definition, then it will become permanent. So if you just see a definition as a definition, and if you study and you just imagine you read it and you don't exercise much on it, then definitely you will forget it. I'm sure. Yeah, you, you
Okay,
understand
sir.
what I'm saying? Yeah.
Understood. Yes,
Yeah.
sir.
Okay. Right. We'll meet next week on Monday. Yeah.
Okay. Okay,
See
sir.
you. Man.
Thank you, sir.
Bye.